Today I'm going to talk about ZJIT, which is a new JIT compiler we are building for the Ruby programming language. I'm Takashi Kokubun. I'm on the Ruby JIT team, which is part of the Ruby infra team at Shopify. We have like 40-ish people working on Ruby-related OSS, and Ruby infra team is like part of it. And then we have like 7-ish people working on JIT, and I'm one of them. I had also been working on like Ruby JIT for like 8 years, like even before Shopify started working on Ruby JIT. So like, and then I've kind of either authored or maintained 5 different Ruby JITs. So yeah, I'm kind of addicted to optimizing Ruby. So I'm gonna provide a background, assuming some of you have not written Ruby, but how many of you have written Ruby before? Any amount of Ruby? Thank you. Many of them you have written Ruby. So it's an object-oriented language, not just object-oriented, but also pure object-oriented language, which means anything in the language is object. Like, for example, integers are also an object and could be modified, and like, there's no primitive types like Java, for example. And that's also dynamically typed. Like, there's no type signature in the function declarations, or variables don't have also like type of signature. So if you have a variable or argument, that could be any type, and that allows the dispatch of anything. So let's say you have a variable and you do a method call on it. The receiver could be any number of different types. So you need to sometimes do the dynamic dispatch even if you specialize that in the JIT code. There's also a lot of meta-programming features, such as notably eval or any programmatic access to almost every part of the language. So to give you an example, this is a 1+2, but as I said, everything is an object, so integer is also an object, and this is object-oriented programming language, so like this is a class definition for the every integer, and it's also open class. You can redefine any method on the class at any time. So integer plus could be different to like something else, like returning thousands here. Another example here is this is also dynamically typed. So as I said before, the variables or arguments can be any different type at any time. So if you give a integer 2 to this like integer plus looking code that returns 3, but you could also return random class you define, and that same the method needs to handle different classes there. I'll give you some other features that make it hard to optimize. So here we define the local variable n equal 1, and then print it. But there's, as I said, there's an eval. So like, and then eval is also not a keyword. So any random method call with a string argument could modify the local variable. And there's also programmatic access to local variables or any other like type of variables, like for example, instance variables also have a programmatic access. So this binding is a method call as well. Like Ruby allows you to call a method without parents. So binding is a method, and then it evacuates, escapes the local variables to the heap. So it returns a binding object that has every local variable, and it allows you to call this local variable set method that modifies the local variable n in the heap object. And once you escape the binding, then that frame will refer to the local variables in that heap object. So the caller method will be able to see the local variable set by the local variable set. And another very bad API for optimization is that you can also get the binding object of caller frames. So whenever you call a random method, that could also call another method that could like escape the binding of caller frame. So whenever you make a method call, you need to be prepared for every local variable in the frame is modified. And there's also a tracing feature that allows you to do that kind of thing. So like in this last example, whenever you go to the next line, that triggers the line event and increments every local variable in the top level frame. So we are dealing with that kind of stuff. And there are three major Ruby implementations that are relevant today. So like there's a CRuby, which is the thing I'm going to talk about mainly today. CRuby, as the name suggests, is written in C. It has a stack-based interpreter. The bytecode is stack-based, and the JIT is a retrofit, so it's still not enabled by default. If you just run the Ruby command, it doesn't enable JIT. Another thing is JRuby. So JRuby, the J suggests that it's a JVM-based implementation. The Ruby source code is parsed into the bytecode for the Java virtual machine. And because JVM has a JIT, it can JIT the bytecode. There's also TruffRuby, which is originally implemented in JVM, but also has an AOT that can compile some of the implementation to the native code and starts with the native code and then also runs the Ruby scripts with the JVM. And TruffRuby has the best peak performance out of all these, but we still invest in implementing our own JIT for the CRuby. Which is because all these other implementations have some things that are not suitable for our use case at Shopify. So for example, JRuby is implemented on top of JVM, and as a result, it doesn't support the C extensions today. It used to support, but it stopped supporting them. And we, Shopify, use C-based or native-based libraries such as gRPC. So we use a Ruby library that has a binding to the native library, but on JRuby, you need to rewrite everything in Java or Ruby, so it doesn't suit our use case. And for TruffRuby, it supports the C extensions. They compile C into their bytecode by LLVM. So that works, but it has a very slow warm-up, partly because they have AST-based interpreter. So if you run TruffRuby locally, for example, if you want to install libraries, Ruby libraries, the local command generally runs very slow compared to CRuby. So this is a usability issue if you run the show command locally, or even in production, it uses a lot of memory because of their very advanced optimization. So the peak performance is good, but it's too much memory usage. So we are kind of sticking to CRuby. Though the key difference here is CRuby has a GVL, two other implementations don't, but because it has a GVL, we usually are forced to use a multi-process servers. So on the boot of the application, we fork processes, and CRuby may use a lot of memory for each different workers. So even if the single process uses less memory in CRuby might use more memory compared to other implementations. But today at Shopify, we kind of built our own server, Ruby server, HTTP server that is able to periodically fork another living worker to another process. So that triggers a copy on write efficiency. So that original worker shares the memory with other workers. So with that, CRuby has the most efficient memory usage out of these options. So we have a fast warm-up and a small memory footprint, so which is why we're kind of developing a JIT for CRuby. This is a paper we published 2 years ago. We presented it at the MPLR 2023, and that gives a comparison between the three different Ruby JITs, the implementations on memory and warm-up. So if you're interested in the actual comparison, you might want to look at the paper. So about CDB. So CDB, going forward, I'm going to mainly talk about CDB by just saying Ruby. So the first Ruby JIT that we merged to the upstream like CDB implementation was called MJIT. So MJIT was uses sort of template JIT. So like we have virtual machine implementation, the bytecode implementation. So each bytecode has a C code that implements the bytecode. So we have kind of print the C code in the virtual machine into like when you look at the instruction that prints C code, C code, C code, C code. So like stitched together and then kind of eliminates the dispatcher overhead. That also supports compiling the C code with the major like C compilers we wanted to support, mainly like GCC and Clang, but there's also like Windows maintainer who insisted on supporting it, so we also supported the Microsoft Visual C++. That was originally written in Ruby, then we kind of rewrote it in Ruby, but that was mainly C-based implementation. That was good in terms of like some micro benchmarks. For example, if you have a while loop converted from Ruby to the C code using the template JIT, that was able to sort of compile time, calculate the, for example, the increment of the local variable in Ruby, but that didn't go well in terms of, first of all, one issue was the compile overhead. So like, whenever you compile a method, you need to spawn a process of a C compiler, and that takes time compared to other like JITs that we have implemented. So the compile time was a sort of an issue, and also we didn't get to optimize the main use case of Ruby, which is web applications. So Ruby is kind of known for its framework, Ruby on Rails, but MJ didn't do well on the Ruby on Rails framework. So we wanted something else that optimized that well. Part of the reason why MJ didn't go well is because you need to kind of give some information that C compiler needs for optimizing the logic, but generally the C implementation for the interpreter is kind of dynamic everywhere, so C compiler cannot figure out how to optimize such dynamic dispatches, for example. Unless you inline everything and provide every memory, but at compile time, that's usually not available. So the only optimizations we added on top of the template JIT is we sometimes replace the template with something that uses the inline caches and then reads the inline cache and then replace the method dispatch with the optimized method dispatch. But that was not enough to speed up the Rails, so we moved on to try another implementation. So YJIT is the one developed by Shopify at the Ruby 3.1 that uses a so-called lazy basic block provisioning technique that was originally proposed by the PhD paper of the developer at Shopify, who, in her PhD thesis, Maxime. So like, that was in process compared to MJIT. So like MJIT relies on the C compiler, but the YJIT doesn't. It has its own assembler and converts the bytecode into its own IR, and lower level IR that abstracts the backend. And then it's written in, was originally written in C and then written to Rust. And then we also had another JIT called REBASE'25 that was written in Ruby that has a similar architecture to YJIT, but we added that so that there were some like Ruby developers who were interested in contributing to JIT. So by rewriting, like having the Ruby JIT implementation in Ruby, we kind of allowed them to sort of hack on the JIT compiler itself by opening the class of the JIT compiler, and then that was sort of a way to let the users of Ruby develop a JIT compiler by themselves. The last thing, the main topic of today is the ZJIT. So because we weren't sort of, the YJIT went well, but we wanted to do things that aren't really easy in YJIT. So we kind of came up with another design that allows you to do cross-instruction optimizations, which is a SSA-based IR, which has a SSA-based IR that was not available in YJIT. So like YJIT was like one pass from like bytecode to the low-level IR, but ZJIT is like bytecode to high-level IR, which does the language-specific optimizations, and then low-level IR that is the backend. So as I said before, YJIT was a lazy-basic provisioning-based implementation developed by us, Shopify, and not enabled by default in Ruby, but in the Rails is the most popular, the Ruby web application framework, and that enables the YJIT by default from the Rails version 7.2. So it's kind of like the production REBASE'25 out of all Ruby JITs in the CRB so far. And because it's not enabled by default, sometimes when people compare the performance of different languages, they don't enable YJIT by default, so they get like slow performance. But if you, by the way, we kind of had a patch that enables YJIT, but then that improves the performance. It's still not competitive compared to like other pretty optimized dynamic languages such as JavaScript, but it's not as bad as like this original graph. They never update their website, so it's not updated on their website, but if you turn on YJIT, it's slightly better. Though we wanted to do better than this, and we kind of decided that we need some different design for making it faster than this. This is the original lazy basic provisioning paper. So if you want to read how that works, you might want to check this out. The reason why we are building the REBASE' here is like Shopify is the sort of the larger company that uses Ruby by the market cap. So we kind of invest a lot in the Ruby ecosystem. And this is the website that lists only the public companies, but there's also a private company that kind of uses Ruby, which is GitHub. So GitHub also uses YJIT in production, and then they saw 15% to 25% speed up in the production. It might not seem a lot, but for Rails applications, it's kind of a lot. I mean, I'm going to talk about that later, but generally, the community has seen 10% to 20% improvement when they turn on the YJIT flag. So sort of they get those kind of performance improvements for free, basically. So they're kind of de facto standard at this point. So ZJIT, this is what we are building today, this year. So Ruby is an annual release, and we release Ruby on Christmas. So like it's 2 months away from today, and then we are sort of we started development in February. So like it's still very in progress. It's not like ready for evaluation, or even though we need to release that in 2 months, but we want to make it at least comparable to YJIT in the next release, upcoming release. So we started the development in February and then passed the CB test suite in September with the base of like the IR-based optimization, and also making the optimization compatible with the dynamic features we presented before. So we have a nice infrastructure to start optimizing the language, but this is the current status, so we don't have the benchmark graphs for ZJIT today, but we're going to discuss the designs we want to sort of release this year. So I'm going to talk about the main topic, why we started developing ZJIT. We wanted to develop ZJIT mainly because YJIT wasn't able to do the cross-instruction optimizations. So because YJIT does the lazy basic group versioning for providing, it stops at many places for providing the virtual machine stack and local variables and method definitions. So it sort of splits method into multiple pieces of the blocks, and then each block is compiled separately. So it's generally harder for that design to optimize across different virtual machine instructions. And also, because every basic block was compiled lazily and it needed to have the metadata allocated on the heap, we had to sort of be aware of, sort of design what's in the metadata for minimizing the amount of memory we use for YJIT. But because we compile that per method now, we no longer need to sort of care for that this time. So I'm going to go over how YJIT works. YJIT, so like Ruby in general has a bytecode and then compiled into this kind of bytecode, which is stack-based. So like put objects pushes the object 1 to the stack, and then get constant gets the object constant 2 to the stack, and then the send is a method call instruction that pops the 2 objects from the stack and then dispatches the plus method, and then returns the result 3 to the caller. So YJIT, because of the invalidation reason for the constant, it needs to split the block for the get constant instruction. So it stops at the compilation after compiling the put object. And so because it's only compiling the put object 1, it needs to assign the put object 1 to the register. And then the next block just get the constant and then assign that to the register with the patch point so that you don't need to roll the constant from the heap. And then finally, we have the third block that's just adding the 2 registers and then return that with the patch point of method redefinition so that we don't need to like check the redefinition every time. So because of this architecture, those 3 blocks are compiled differently, and we weren't able to even constant fold 1 plus 2 into 3 because they are sort of compiled separately. It's not a limitation of the lazy basic block versioning itself, but it's more about we wanted to save memory, so we didn't add the, for example, object value like 1 or 2 in the metadata. So as you can see in the context, it only saves the integer type and not the value itself, like 1 or 2. We could have saved that in the context and then do that, but because we sort of wanted to minimize the memory, we didn't prioritize optimizing that. So that's what's happening today with YJIT. So for ZJIT, we have a method, the architecture. So we are going to compile the bytecode, the whole bytecode of the method at once. But to do that, because we, unlike YJIT, we don't do the profiling in the as the like a lazy compilation. So to profile all the types, we have this ZJIT send instruction. So like whenever a method is called some like multiple times, then reaches some threshold, it converts the instruction that needs profiling data. For example, send, the method call instruction is converted to the ZJIT variant that does the profiling. So whenever the interpreter runs the profiling method, that saves the type information that will be used by the compiler later. So that will allow the ZJIT to compile the entire method at once. So with that profiling information, ZJIT is able to compile the whole method at once. And then we have this SSA-based IR. So V1 and V2 are not really compiled into the actual code, but it's there so that we can generate the side exit for the patch point. So like, and when the constant 2 is invalidated, we need to write the object 1 to the stack, so that's there. But for the actual generated code, that's able to constant fold based on the SSA, and then just return 3 as the generated code, and with the patch point that's for the constant redefinition or method redefinition. So I'm going to talk about the main challenges in optimizing Ruby and how we are planning on sort of fixing those problems. The first, the kind of like the main bottleneck in Ruby is that C functions dominate execution time. So like we have, so CRuby is written in C, but also, like this library of CDB is mainly written in C, so the benefit is that you have a very good warm-up performance, but on the contrary, when you JIT everything, then JIT is not able to optimize across the C function call boundary, so like it kind of limits the ZJIT to from optimizing Ruby further from like changing the behavior inside the C function. Another thing is local variables are too dynamic, as I showed before. That kind of has limitations in optimization. We kind of deal with that by invalidation, but it still has things to be done there for optimizing it further. There's also method calls, and because of the dynamic nature of the language, it's pretty slow in the interpreter. And also, even in YJIT, we still execute a lot of instructions, so that's slow. So for the first thing, the C functions dominate execution time. This is the benchmark graph that's before the ZJIT that compares the YJIT, RJIT, and MJIT. These are the three different Ruby JITs that were merged to Ruby before ZJIT. Then you can see so like this is a set of the benchmarks that are like sort of representative of the real world use case of Ruby, which is Ruby is kind of popular for the Ruby web application processing. So these are kind of web related benchmarks. And then in any of these, all these existing Ruby JITs didn't achieve the twice as fast as the interpreter. So there was some comment from Ben that said like JIT should generally give a 10 or 2 times faster than the interpreter, but it wasn't achieving that performance. The reason why is obviously, I mean, in the CDB, even with the YJIT, only 10% of the execution time is spent in the JIT code. If you benchmark applications such as, so we have a benchmark called Lobsters, which is a Hacker News-like website written in Ruby on Rails. And in that benchmark, only 10% of the cycles are spent on the JIT code. So even if you make the JIT code faster, that will obviously not make it overall performance at 10 or 20 times faster. The reason why we spend that few cycles on the JIT code is because we have a lot of polymorphic call sites that will kind of force the JIT to sort of resort to dynamic dispatch. So let's say there's a call site that needs to handle 100 different classes, which actually does exist because the framework has providing base class, and then every user of the, for example, there's an active record class, and then there's an active record base class that's sort of used by so many models that are used by the application. And every single one of the model is going to call into the base implementation that ends up being the megamorphic call site. So that's kind of common in the Ruby programming language. And because we don't want to inline those hundreds of different classes or even more, after trying like 4 or 5 entries of the inline caches, we sort of fall back to the dynamic dispatch. And in that case, we kind of reuse the interpretation that's written in C. So that's out of the JIT code execution. The same is true for instruction variables. The second one is called IVARs. It stands for instance variables. Instance variable uses object shapes-based optimization, but because that's shared across a lot of different classes, that could also go megamorphic, and that ends up calling the C function for handling that kind of case. And because it's a web application, there's some DB queries spending some time in the benchmark, so 15% is going to be not going to go away, even if we do anything on the Ruby JIT. There's some cycles, of course, spent on the GC, but that's some of them could be optimized by our effort in optimizing the language if we stack allocate the objects, but YJIT still hasn't implemented the stack allocation, and we haven't done on the ZJIT yet, so that's something to be done. But basically, probably many of them are going to be just escaped anyway in the language, so that's still going to stay there too. And majority, I mean, a large amount of cycles are also spent on the C-based implementations of method. So like there's a string, hash map, and arrays, and also the hash table implementation called ST. So like we do specialize many of the popular method calls on those classes, but we still had to sort of reuse the C-based implementation for implementing edge cases or calling into other like non-so-frequent operations. So as shown here, methods are written in C, and also like when you call into Ruby from the C method, you need to do a lot of setups for setting up the environment for the virtual machine or JIT code. So it has some overhead that needs to be done in the C. And also, as I said before, megamorphic call size also required JIT to spend time in C functions. The approaches we are thinking of are, one of them is, of course, rewrite things in Ruby. So when things are calling into Ruby from C, for example, when a method takes a block that needs to do the overhead of like crossing C to Ruby, so in that case, it's generally, even for the interpreter, faster to rewrite those kind of things in Ruby. So in this example, we just rewrote them in Ruby. But in some cases where the C is actually faster, even for the methods that take block, we just guard with JIT helper that allows you to define the Ruby version of the method and the C version, and sort of maintain two different versions, and enable the Ruby version when the JIT is enabled, which is the current approach. For megamorphic call sites, what we are thinking is we, I think, sometimes need to copy the megamorphic call sites. For example, when there's a loop method that takes a block, the loop method implementation could be copied to the caller of the loop method, and then that will allow the loop method to not make it a megamorphic call site. So like the block is also sort of a method call in the CV implementation. So that will also be megamorphic if you don't copy the array each, like a loop method. But if you copy those kind of loop-related methods, then I think the megamorphic call site could be also optimized by the JIT code specialization. For local variables that we showed earlier, YJIT spills every local onto the VM stack so that will support the heap-based modifications of the local variables, like we showed before. But the C calls and any Ruby method calls also do the spill, and that's kind of how we deal with the dynamic nature of the local variables in YJIT. But in ZJIT, we are kind of changing it to spill that onto the C stack, so that the access will be at least more localized compared to the other native instructions. And then we gave up on making the local variables live in the register in the YJIT on every C function and call, and also a lot of methods are written in C. So spill happens a lot in YJIT, but in ZJIT we push pop the registers across different C function calls. So these are live, and that allows us to sort of fast access to those local variables in ZJIT. So lastly, I'm going to talk about how the method calls are very slow in the YJIT or the interpreter. So this is the native instructions that YJIT generates for the fastest type of very simple method call, but it's still a lot of methods, the instructions. So on every method call, it spends cycles for this amount of instructions. First of all, we need to check the receiver class, and then also Stack Overflow check to raise a Stack Overflow exception. And also, we spill registers on the YJIT, and then the majority of the time is spent on the frame method that allows you to implement the dynamic nature of the language. So these are a lot, but our idea for ZJIT, or what we are planning on in ZJIT, is that first of all, we drop the metadata instructions by writing the base pointer to the virtual machine frame, and then lazily reading that off of the virtual machine frame and sort of materializing that lazily. So it's easier to be said than done, but like we need to do a lot of things to sort of make it possible. But yeah, we are working on it to also, yeah, make it possible. Because if you dump the instructions for YJIT, oftentimes the method call overhead is sort of dominant in the assembly. So if you optimize that way, the method call overhead like this, I think it's going to be much faster than YJIT. So that's what we are currently working on. So in conclusion, we are building a ZJIT so that we can unblock the cross-instruction optimizations, and we discuss the optimizations we are thinking of for C function calls and like local variables and method calls. That's it. Thank you.
Are there any questions?
My understanding of the lazy basic block versioning is it also was designed for being very low latency. Have you, I guess, do you have numbers for the new JIT to compare? But have you also considered tiering up from YJIT to ZJIT? I don't know if I got the letters correct, but.
Yeah, I think these are good questions. So like for the first one, we've seen the comparison time overhead as well, and then that was sort of comparable. Like it's still not slower than YJIT, but the caveat is that we still have things that are not supported to compile. So like the amount of things compiled in YJIT and ZJIT are not the same, so it's not the right time to still evaluate them. But as of now, it's pretty comparable. So like ZJIT is also low latency, maybe because we still like have a very similar backend in the lowering of the instructions and also do the similar optimization. So essentially, they kind of go through the same kind of optimization. So that's why they are comparable, I think. For the second question, we also somebody's mentioned the idea of tiering, like for example, providing in the YJIT and then the ZJIT. But the downside is that the memory overhead. So like even with YJIT, people are sort of because the memory is often a bottleneck in the production use of the Ruby. So we want to sort of minimize the Ruby memory usage, and by tiering them, you need to spend some memory in the JIT code, and also the metadata. Actually, the metadata for YJIT compilation is twice as or 3 times larger than the JIT code itself. So we anticipate that if you tier them, a lot of memory is going to be spent on just for providing, which is why we chose the current design.
Peak memories or steady state?
Steady state. Peak is, fine-ish, but yeah. So even in the peak, because the YJIT does the lazy compilation, you need to keep the metadata forever, basically. So the peak and the compilation generally affects the peak as well, unless you completely change the design of YJIT.
So clearly I need to watch what I say on the Hacker News. Sorry about that. So it's good that you're measuring in context with big benchmarks that do real things. But one thing I'm curious about is how it performs on micro benchmarks. And those have a specific role. Those get rid of the noise of everything that's not your JIT, and that will help you scale up. But maybe you have those numbers?
I do, but I'm sorry. That's so like in the Ruby. Sorry, I wanted to open the browser, but didn't work. So like we have a benchmark suite called Ruby Bench, and the graphs I showed earlier was one category called headline benchmarks, and then we have 2 other categories. There's other categories that's smaller than this and not the web-related application, and the last one does actually micro. So we have micro benchmarks, and then half of them currently have a very similar performance to the YJIT currently. None of them is currently faster than YJIT, but we've seen things that became faster than YJIT, which is we had some annotations that allow ZJIT to eliminate the method call or inline especially some of the C function calls. So in that case, that was faster. But right now, because we are sort of dealing with the problem of splitting everything on the virtual machine circuit. So like in the last section, I discussed the idea of lazy splitting things to the virtual machine stack later when needed. So once we implement that, we are sort of expecting micro benchmarks to be faster than YJIT, but as of now, because we haven't done that yet, that's generally either comparable, almost the same, or just slightly slower than YJIT, which is the current state.
Hi, thanks for the really great talk. It seems like, especially in the Rails context, there's kind of a lot of code that, like you had mentioned with Active Record, that is kind of pathological, that does things like defeating polymorphic inline caching. Do you think that there's a role of extending the Ruby language to almost disable some features? I know earlier in the session we had Carbon, and a lot of that was kind of being able to roll back features from C++ in order to make it more memory safe. Is there a role of a restricted Ruby language that restricts things like the dynamism that you pointed out before, specifically for those small, very hot areas, such that you could get a more reliable performance from those?
Even the language author Mats considered such kind of design as well, but there's an issue with that. So, like for example, even if you remove the binding feature, for example, like that allows you to access local variables, it just costs us some memory because like we could still invalidate the local variable access by having the invalidation point, and then when the binding method is called, we can invalidate such kind of things. And for the mega-config call sites you mentioned, I think it's sort of a very core feature of Ruby. Like if you can't duck type the classes, then kind of loses the point of object-oriented programming. So because Mats is kind of in favor of the programmer happiness in general, I don't think that particular, like the megamorphic call site part is not going to be solved. So I think we still have to like fix the problems by ourselves. And also personally, I'm not a fan of like modifying the language for the performance. So like I think I still believe in Ruby could be pretty fast without modifying the language semantics. So I still want to keep optimizing that until hitting the wall. That's absolutely not impossible to optimize. So right now I think we should just duplicate the body of the megaconfig call sites, and then that should, I think that there's a problem.
Great, thank you.
So thanks. I think we are running a little bit out of time, but okay, last question.
You were saying GC on that benchmark was 15% of the time. What does that mean? Like, what is your GC architecture? Are you guys like actually like every int is an object in Ruby? Are you actually allocating an int object every time an int is used, stuff like that?
So we have, despite the semantics being the object-oriented language, there's still immediate like implementations for some types. For example, integers have a fixed num representation that doesn't need to be heap allocated. So for example, the 1 + 2 doesn't allocate anything. The GC time spent here is like, this is the Linux perf script integrated with the Linux perf, and then we sort of analyze the use of time spent in C functions based on the name of the function. And then this GC category is based on either the name has alloc or free, or ZC underscore something. So like allocation and free, and also the GC mark and sweep are included in this category. So
is your GC stop the world?
No, it's an incremental marking, and so generally, if the minor GC runs, it doesn't spend a lot of time. And in this Ruby benchmark, we've seen basically no major GC in the benchmark iterations. We sometimes see the major in the warm-up iterations, but that's not part of the benchmarks generally.
Is it concurrent or?
Not concurrent.
Got it.
Okay, thanks a lot.